Okay, now we know what we mean when we say convolution operator, and we have seen some examples. The next thing we want to do is understand invertibility and hence the spectrum of convolution operators. And here you just need to know one trick, and then the rest is simple. And that main tool is the Fourier transform. We spoke about it in section 3.3 in one of the examples, example 3. And the Fourier transform takes a capital L2 function on the unit circle in the complex plane and maps it into the sequence of Fourier coefficients. So please check back to example 3 in section 3.3. But what the Fourier transform does, the way we defined it, it takes the Fourier expansion, which is a power series with, well, actually people call it a Laurent series because it also goes in the negative direction. And the variable t is running around the unit circle, which is why most people write it as e to the I phi, and then you get e to the I k phi. And if that's your function, then the Fourier transform just is interested in the sequence of coefficients, so-called Fourier coefficients, and that's then an element of little L2 over the integers. And it turns out that this is an isometric isomorphism, so it's compatible with plus alpha times, and it even preserves the norm. And one property of the Fourier transform that is particularly important to us is the so-called convolution theorem, which says that the Fourier transform turns convolution into multiplication and also vice versa. So it also turns multiplication into convolution, which follows from the fact that the inverse of the Fourier transform goes by almost the same formula as f itself. There's just a minus sign in some place. So let's draw the following diagram. So we want to understand our convolution operator LA between these two sequence spaces, little L2. And in order to better understand that, we change perspectives on both sides here and here via the Fourier transform. And then by the convolution theorem, this change of perspective turns our convolution operator here up here in the blue world into a multiplication operator down here in the red world. But we're not quite sure yet by what function is multiplied down here. Maybe we could call this unknown function here little b, and then try to find out what's the matter with b. So let's start with some capital L2 function on the unit circle over here. Maybe let's call it little f. And then the result after multiplication by b will of course be just b times f. And now the convolution theorem says that the Fourier transform of b times f is just the Fourier transform of b convolved with the Fourier transform of f. Well, actually, depending on how you define the Fourier transform exactly, you sometimes get some ugly little factor here, but let's not worry too much about this for the moment. Now, the Fourier transform of f is the point, let's call it x, that we're interested in up here in our sequence space. So it's the sequence of Fourier coefficients of f. And the Fourier transform of the result, b times f, is just the corresponding result of our convolution operator up here. And let me write a star x instead of operator LA applied to little x, which is the same. Okay, but then it's clear what has to go here. This has to be A. So we get that A is the Fourier transform of B. And many people abbreviate the action of the Fourier transform by a little hat. But now A is given and we want to express B in terms of A and not in the other direction. So let's agree on the following convention. Let's write little a with an upside down hat to denote the pre-image under the Fourier transform. So with this notation we can replace B by a upside down hat here and here, and then here for f we can write x upside down hat, and then this here is a upside down hat times x upside down hat, which is just a star x convolution and then upside down hat. So as a rule for the Fourier transform going up you're using the hat, and for the inverse Fourier transform you're using the upside down hat. So just like the direction in which the arrow points, you're placing your little hat. And then we could denote this multiplication down here by m, and then it is multiplied by a upside down hat. And we could summarize the message of this little diagram here as follows. Our long operator or convolution operator, which takes us from x up here to a star x over here, can also be written as Fourier inverse down here, then multiplication by a upside down hat over here, and then Fourier transform up here. And of course you know that you have to read these products from right to left. Okay, that's what the convolution theorem is doing for us. It lets us rewrite a convolution as a multiplication, of course with these two translations, Fourier transform and inverse Fourier transform, between the blue and the red worlds respectively. But once you've understood that, then it's very easy to talk about invertibility of this convolution operator, because it's invertible if and only if the multiplication down here is invertible. Because what happens here and here is just an invertible change of perspective. So if this red operator is invertible, then the blue one is going to be invertible because it's multiplied by invertible here, invertible there. But of course you can also rewrite red as blue with a little bit of green from the front and the back, and then argue just in the other direction. So if blue is invertible, then red is going to be invertible. Okay, but when is a multiplication operator invertible? When can you undo the multiplication by a certain function? Well, if and only if that function has no zeros, because then you can just divide. And that already settles the invertibility problem. So now let's talk about the spectrum of the convolution operator LA. Well, a complex number lambda is in the spectrum of LA if and only if the following operator is not invertible. And of course that operator is L of A minus lambda times identity. But now let's transform the convolution into a multiplication here again. And then let's rewrite this identity here by f times f inverse. And then factor f out to the left and f inverse out to the right. And actually this identity here should be red now. And then you note that this lambda times identity is also a multiplication operator. It's just multiplying with the constant function lambda, and then you write this as multiplication by the function a upside down hat minus the constant lambda. And then you're back to a single multiplication operator here, of course sandwiched by Fourier transforms back and forth. Okay. Now, of course, that operator here is not invertible if and only if this multiplication operator in the middle is not invertible. But we know what that means. It just means that this function you're multiplying with has a 0 on the unit circle, right? So this time it's about not being invertible, so it has a 0. And let's spell that out more explicitly. There exists a point t on the unit circle such that this function evaluated at t, which means you're evaluating the function a hat and you're subtracting the constant lambda, gives you 0. Then you simply rearrange that and reformulate a little bit. So lambda is one of the values that is attained by the function a hat when t is running through the unit circle. This is exactly what you say here. But of course, this here is just the image or the range of the function a upside down hat as a function over the unit circle. Or you could just say the image of the function applied to the whole unit circle. Okay, I think we can all agree that we are finished now because we said that lambda is in the spectrum if and only if lambda is in that set here. So that set must be the spectrum. Excellent. And I mean, that sounds like a result that we could try on our examples.